Hey, nice to see you again. Here we're going to do some modelling, empirical modelling this time, where we're going to take some data from experiments like this here and see if we can describe it mathematically. Well, there's a description, there's a graph, and we might also like to write a formula for it. What a mess I've got here with all these 5 other graphs here. These are graphs I guess you might obtain from data sets like this, and generally we won't always have y's here, will we? We'll generally have a letter to represent the actual parameter within the problem. The variable within the problem could be numbers of bacteria, population, numbers in the population, something like that. You'll notice here the book has used, Hayes and Harris again, have used T there, have just used X here. So we're going to be focused on, in this utility math subject, in modelling where we have got a practical situation, not just Y and X land. So I want you to look carefully at the 5 graphs. In particular, I want you to look at the data points in blue there that have been plotted. All these models, these graphs, are a different shape, but they do have one very, very important thing in common about those blue dots. Can you see it? You might want to pause the presentation and just have a look at those dots. Anyway, having done that, did you get it? I think there are 2 points that we need to make. And the first one is that the data points will lie such that the independent variable that's on the x-axis is going to be greater than or equal to 0. Because in practice we don't usually, and this is a utility math subject, remember, practical subject, we don't usually have variables which can be negative. So this means, remember, the positive values only for that independent variable that's on the x-axis. The dependent variable, which is on the y or vertical axis of independent variable, is also greater than or equal to 0. That is positive. So what am I talking about? The points always lie up there. Here, just in that bit. Can't go past 2 in that case because there's a graph with an asymptote. And here, can you see there are no points there? Because in practice, if you're measuring something, you get positive values for time and positive values for your dependent variable. Same thing here. Can have a value x is 0, but it can't be in the negative region. So quite often we would shade those quadrants in, saying that they are going to be not within the domain and range of this function. If you remember the first exercise there in chapter 2, talking about domain and range. Where can a function exist? Well, on top of where it can exist, we need to make it practical in the context of the question. Practical, look at the context or the situation in which the mathematics is going to be applied. So keep that in mind. That's extremely important in this course, to be able to talk about the limitations, the extent to which the model will be appropriate. Okay, so what have we got? We've got 5 little graphs there. What sort of formulas produce graphs like that? Because they're going to be our tools. What do you reckon this might be? What sort of function would give that sort of result? You can see here we might be questioning whether it's possible to get negatives there for y, but of course it could be, couldn't it, if these were temperatures or something, because you can go below 0 in temperatures. So it's not absolutely true that the dependent variable is like that and independent variable also, but by and large it is in our practical world. Okay, let's go down and look at some tools. Let's see if we can get some formulas for these different shaped graphs. So here are your tools, and I've taken this from Hayes and Harris. Again, of course, where they have a very nice description at the end of that chapter 2, where they're talking about modelling from data or empirical modelling. So I think we can give this one a tick. A straight line is of the form y equals mx plus c. Don't forget here we've got t as our variable name. More practical might mean time, for example. Quadratic, we've done them pretty well. There it is, the formula for a quadratic. This is convex or concave up. We probably use the word convex. This is concave. Why? How do you remember a cave? Well, I'll put you in a cave. There you are. You're sitting in there, in the cave. Okay, so that's not a bad way of remembering concave. So it depends on the coefficient of the squared term, the number in front of the squared term. If this number a is a negative, then you're going to get a cave to live in. If this number is a positive, it's going to be a convex shape. Alright, so that's a bit of revision. What are we doing? We're trying to study the formulas or formulae which are going to be able to describe the pattern of the points and plot as the graph that we get when we do this. How are we going to get the graph by and large? We're going to use technology, so we're going to do that in a minute. Just revise a bit of that. Well, our next tool, our next function for modelling is the power function. Now, some people confuse the power and the exponential because, of course, those two terms, power and exponent, are often interchangeable, but not here. The power function is when you have the variable raised to a power. There's the power there. So a power function is the variable raised to a fixed power, if you like. Okay, so that's a power function. We'll have a look in a minute at what the exponential function looks like. So what are the characteristics of this? If you have a positive power, and that's generally what we'll be using, so if the power is positive, the function passes through the origin, so it's these first two, this one here, greater than 1 or between 0 and 1. Quite a different shape here. Between 0 and 1 means the power will be a fraction, but we're still talking about a positive value. So you get these two different growths. And then here, if m is a negative, so that's going to mean t to, or 1 over t, so it's going to be a decreasing function. You have a negative power. Do you remember that? Let's take something like 2 to the negative 3 means 1 over 2 cubed. So this negative actually causes us to look at reciprocal or create a fraction, so it's going to go down like this function here. Okay. If m isn't a whole number, the graph may not be defined. So we don't see too many of those. Can you see that it is possible and usual for the graph to go through 0? Because when t equals 0, a times 0 to the m equals 0. Okay, substituting t as 0 in the function. So it's passing through the origin. T is 0, y is 0 in that case. What about the exponential function? What's the difference? Well, here, can you see the variable is the power itself? Whereas up here in the power function, the variable is raised to a power. Variable being t here. Down in this one, the variable sits up in the power. And so we've done a bit of this back in year 11. So here's a characteristic when b is greater than 0. So what does that mean? Well, we put a number in front of the t, the variable there, bt. So if that's a positive power term, it'll be exponential growth. If it's negative, for the same reason as before, let's look at that. E to, let's say, something like neg 2t. What does that negative mean? It means the reciprocal. So really we're talking about 1 over e to the t, and if this is a fraction, it's going to give us a decreasing function. Now, this is the first time we've seen the number e, and Hayes and Harris say they've described it previously. Well, I haven't got this on here, so I'm going to say that e is a very, very important base power. It's between 2 and 3 in size, and it's called the exponential. So it is very important. It's an irrational number, it keeps going. It's approximately 2.718, etc. We're going to look at that closely in the coming chapters, because in calculus we see the importance of this irrational number. So for the moment, I want you to know it's a non-terminating, non-repeating decimal, so it's irrational, keeps going forever, those decimal places, and so it can be rounded off to 3 decimal places, 2.718. Now we'll see later on why that's important. Now, just make sure you remember this, that as t tends to infinity, if the power expression containing the variable there is positive, that's going to keep going up. If it's negative, it's going to get smaller and smaller. So this one here. So let's just discuss what's going to happen to this as t gets very, very large. Well, this is a fraction. So as t gets very, very large, you know a fraction times itself gets smaller and smaller. It's going to tend to 0. And so we have an asymptote at y equals 0 as t tends to infinity. An asymptote is a value that the function approaches and generally never meets in that vicinity. Of course, a function can be asymptotic in one region and then somewhere else cross that asymptote. So we really best said, as t tends to infinity, the graph is asymptotic to y equals 0. You should always put that in. T tends to infinity, y tends to 0 from above here. You should put where that asymptotic approach occurs, in this case for very, very large t. So are you getting the idea? When you see a set of data points plotted, you will go to some of these tools and see how well they fit. And that's what we're going to do in this little unit. Okay, well, I really want to say something about these two. I put these in a different order, by the way, from what Hayes and Harris has, because I want to relate them. I want to relate the power function, which is where the variable is the base and it's raised to a power, and then the exponential, where the variable is the exponent or is the power. And now I want to talk about this statement here and how we fix it up. Populations with unlimited growth are often modelled by exponential functions. But what sort of population would have unlimited growth? If you've done any biology, you know that generally populations are limited by resources available, the size of their environment, the food in the environment, the active predators. So it's very unusual to have a population with unlimited growth. Nothing goes on forever. You've got a question here saying, wow, why would it keep going to bigger and bigger? Okay, and it's unlikely. So what do? Well, we're going to develop what's called a logistic function. If you're also doing specialist maths, you'll find out how this function was actually constructed to describe a set of empirical data. And this is called the S-curve, mentioned before. The S-curve in biology, where we have, an asymptote here, a value that the function approaches, and usually that's due to limiting resources. So here we have been able to make it more practical. The logistics of practical aspects of any task. What are the logistics of this? How do you do it? And so this is a more practical function, if you like, to the exponential function. You can still see it's got an exponential aspect to it. Well, we had to do a few other things here to make it flatten out, if you like, or reach that asymptote, y equals c. So we're going to be doing a lot of things with this, because clearly it's an interesting function for biological applications in modelling populations. And so I want you to look at the sort of properties of that function. We'll be able to draw this easily on our calculator, so don't be frightened by c over 1 plus ae to neg bt. We're going to use technology to attack that. So the graph grows steeply before reaching a point of inflection. So that's an inflection point. We'll be doing that later. It inflects because it's going from what? Convex, slight turn there, to concave. Let's call it a point of inflection. It's a characteristic of these functions. Populations with limits to growth, such as restricted food supplies, are often modelled by that. So I want you to start to get the feel that, gee, getting a few tools here. You know, functions that we can use to describe any data set that we might come across. Let's finish off here with another couple. Rational function. Again, usually we're not interested in that much. It's a function which will have an asymptote, because what does ratio now mean? It's a ratio. Rational means the number or the function can be written as a ratio. So here they've drawn this one, and you can see as soon as you have a ratio, you have problems, because g of t cannot be equal to naught. The overall ratio function, rational function, would not be defined, and so you're going to have an asymptote sort of approach there, and values where it won't be defined. A couple of consequences of the rational function. So the vertical asymptote there, the value of the independent variable that makes the denominator 0. You can't have a 0 denominator. And then a horizontal asymptote. So they are characteristics. So if something's approaching a line like this, you might think, maybe a rational function. There is another function, however, which has a similar behaviour, and that's a logarithmic function. You can see here it is possible to get negative values of this function, a logarithmic function, something like that, but we're finding the log of the independent variable, and here we're using base e. Remember, the log here of 2 implies log to the base 10. We usually write things as powers of 10. The log of a number is the power you raise 10 to get the number. So the log of t, ln, we call that ln, or log to the base e, is the power you'd raise e to get that value t. So what do you notice? Well, you can't find the log of a negative number. I'll write that down. Can't find the log to any base, or to a positive base of any number. Can't find log of a negative number. Why? Because the log is the power you raise the base to. If you raise e, which is approximately 2.718, to any base, to any power, you can't get a negative. Okay, you might say, well, I'll raise it to a negative power. E to the neg a half. No, all that means is 1 over e to the half. It doesn't make the answer negative. Okay, so the negative in an exponent means 1 over. So you don't produce, it's not equal to a negative number ever. So you can't find the log of a negative number. So the log function, for practical purposes or not, mathematically, the log function isn't defined in that region over on the left. Now, I've mentioned the surgy a bit. I rather like the surge function because it has this sort of characteristic behaviour. And what are some practical applications? Talked about one before, where the power is turned off and on again. There's a surge in the voltage and current. What's another one? The uptake of drugs when they're applied. For example, pain-killing drugs. Where would you want the dentist to start the drilling? This might be the level of pain-killing effect up here, getting greater. Where would you want it to be? Please don't hurt me. I don't want you to do anything unless it's in that region there. Is that right? So that's what happens to when you might go to the dentist and have an injection. Then he will wait to at least somewhere here and try to stop working over here so that he's in the maximum, or she is in the maximum pain-killing range. So interesting enough there. And the formula for that is this little critter here. So it does go through the origin, or in other words down here. Why? Because if you put t as naught, you will get y as naught. And then it goes to a characteristic maximum value and then has a tapering off, an asymptote of y equals naught. So again, let's watch this. T tends to infinity, y will tend to 0, and it will be coming down from above. So you can put that there. So it's not bad to be able to discuss what is going to happen from the formula or from the graph. Now don't get too frightened of heavy maths there, or as it appears with the formulas. We're going to use technology, and it's going to help us a lot. Okay, so there are our tools. Now, what are we going to try and do? Remember what we're doing. We're doing empirical modelling, so it means we've gone out and collected a set of data, and the people we're doing it for say, hey, you're a mathematician, please describe what's happening here, and can we then go on and predict what these results will be if we go further, or we want values in between what we've measured. So let's go down then and have a look at a problem. Now, the book has an icon where you can click on it and choose the calculator that you're going to use for instruction there. But what I've done down here is put the Casio steps. So let's go through them. You have collected some data. Here it is. It's what I had up there before. Decide which of the following functions is the best model for this set of data, and there's A, B, C and D. Now, use each of the models to predict values when x is 5.7, x is 20. Comment on the results. Let's do part A. What's the first thing you'd want to do? Well, let's get a graph, because it's going to be hard to talk about whether these functions adequately describe the trends we see unless we see some trends, and not too easy to see trends from a data set. So do you remember? Here's step 1 here. Go to stat mode. Step 2, when you go to stat mode, clear the list, and that's why I've got it on this window. I've used del A to delete all in a column in a list. Then enter the data. There you can see I've ended up with 195.98, the last one here. Enter your data, and then you will hit graph. Don't forget to set it up. When you hit graph, you have an option to set up graph 1, 2 and 3. So you set that up. Our list 1 would be the X list here, list 1, and the Y list would be list 2. And then if you hit graph 1 and draw, here we have the function. So let's go down, and the book has actually given us the solutions here. So let's look at it. There's our graph. I just wanted to show you how we would do it on the Casio. There's the one we just produced on the Casio. The graph shows a scatter plot of x and y, so we're coming over here. Let's look at the solution. So let's go one by one through the functions. It's got a definite curve, so we're going to cross out straight line. Now, the graph doesn't pass through the origin, so it's not a power function. And you see here it's below there because it went into the negatives. So it's not a power function, and it goes into the negatives, so that's another reason for it not being a power function. We won't go into the negatives. Since the graph crosses the x-axis, it can't be an exponential function. So we've crossed all of those out. because it's going down there. Now that's what we want you to do. Think through the models that are available in this course and see if you can see reasons why the properties of those don't fit the data set. Now, having eliminated the functions, we would say, well, this should be the one. So let's put that over the points and see how well it fits. Now, they've done that here, and I want to show you, because you may not have done this before, how we do that. What we're going to do is not get technology to fit its best model. We're not doing that. We're going to look at a proposed model. Someone has said, that's a proposition for describing this set of data. We want you to draw that in stat mode over the points. Now, this is an important technology step here, because see this def G, it means to define a graph. That's what we want. So I want you to hit F4 to define a graph. Up will come graph mode, directly into graph mode, and you enter the function there that you want to put over the top of these points. And then when you've entered that, make sure it's highlighted there and draw. This is what we get. This what the book has got here. The set of points have got that quadratic drawn over the top of them. And so, does it look a good fit? Or I think so. So in discussing a good fit, you might, in addition to what we've done up here, saying why do the properties not fit, but when you see one seems to be a good fit, you could discuss why. Number one, several points on the curve or on the graph of the model, okay, that we're suggesting. So this becomes our model function. It seems to describe that practical situation very well. Number two, the other points are randomly distributed about the line or about the curve, about the model. Are randomly distributed. Can you see there's one above, one below, one above? So, you know, it's not deviating much. The points are pretty well trapped. The model, the curve, have pretty well trapped the points. Overall, all the points have pretty well trapped the curve, you like, on either side, whichever way. So there are some obvious clues here why some models don't fit, because they have properties which this data set is not showing. And then when you do want to check a model and put it over the top, you can discuss those ideas. All right, so if you went back through all the models, you can see here some a little bit different. Here, there's not a lot of difference, I suppose, in all of those. We can see that B and C particularly don't differ much in these early parts of the data set here. You know, from down around X is 5.7. When you get up to 20, of course, there's big differences between the functions. And really then, what is it? B, the quadratic, is starting to be quite different from the other three. And the difficulty with it is, though, the number 20 for X lies well outside the data range, doesn't it? We only went up to 10. 20 is way out here. We'd have to question whether 20 is a good estimation. Why? Well, I don't know. What's the book say here? It says that you shouldn't give an estimate too far off the end of the data set on either end. Why? Because the conditions giving rise, let's put this down, giving rise to the data from t equals 0 to t equals 10. Oh, it's X, isn't it, here? We'll just change that. just get rid of that. From x equals 0 to x equals 10 may have changed. And this is very, very important. You can't presume, just because you measured from 0 to 10 and got a nice looking pattern and fitted a pretty good mathematical formula or model to it, you can't assume that's going to keep going. Right? You have no evidence beyond 10 of what the values will be. Do you remember? That's called putting in extra points, extrapolation, and we say that's not too reliable. All right, so we're going to come to that in a minute. For the moment, I want to just revise something for you, because I think it's important as your young mathematicians utilising these ideas. I've got here a series of steps. We started here with the graph. Now, instead of actually superimposing a function, that's that function there, where you can go back to graph mode and put a function and see how well it fits. What are these here? These are the three windows where you can go searching for different function types and get the calculator to draw it in stat mode. So here, if you want to try and fit a straight line, do you remember? You'd hit X. It comes up with a window, and then you graph it and see how well it fits. If you're trying to fit a quadratic, x squared, or a cubic, you haven't seen that before, so that would be a quadratic, x squared there. So it'd be interesting, why don't you do this, to hit that and see what quadratic your calculator comes up with. And then these others, a quartic, a log function, an exponential function, a power function, a sine function, not in this course. And if you hit, well, you don't hit that. If you want to go to the next window, hit F6, there's a logistic function. So the calculator has on board many different functions, all that we need. It doesn't have a rational function. All that we need there to try to fit these functions to your data set. So if you don't have an actual function you're going to superimpose and check it out, you can get the calculator to try and fit one. I wonder why, and we're going to talk about this much later on. What are the technological difficulties of fitting a surge function to a data set? Maybe you might like to think of the surge formula. It is what? What did we say? AT to the E neg maybe 0.2t. I think if you drew that, you'd find that's a pretty good surge looking function. Now, why might the calculator from a data set of, let's say, y, oops, don't want y up there, do we? We'll put y, did it again, t and y. Think about getting values here, measuring values here, putting it in list 1, list 2. What's the difficulty that the technology will have in producing this? Okay, might come back, well, we'll certainly come back much later in the course and have a look at that. But I'd like you to think about that one, a little bit of a challenge question for you. A bit more mathematical than what we usually get into in this course, but we do need to learn how to handle that function. Let's go down now and pull some things together. Okay, so when we're working with empirical data and we develop a model, some things can happen. First of all, we don't expect, we've got errors in the data, in measurement perhaps, or random variation in the parameters. So those things imply the model is unlikely to be an exact fit. That's the first thing. Not like our deterministic modelling, where there is behind the problem, due to the mathematical relationship between the variables, the parameters which are constant within that system, you will get an exact model in deterministic, predetermined what's going to happen with those quantities. Here we've got things that are suffering random variation. Things like living systems and so on. We got errors in trying to measure those things. So here we are. The model is unlikely to be exact. So that's what we've been trying to do. Trying to fit our best mathematical model to the situation. And then, of course, using the model can be problematic because, first of all, we want to know, well, let's assume it's a good model. Assume a good fit. Like the quadratic back up there before. Assuming a good fit. We want to do two things. Part A, we want to interpolate. Interpolate is saying, well, we measured the population when t was 9 and then when t was 10. What was it? What was the population size at 9.5 years or something like that? Somewhere in between. So interpolation is to estimate values between, values between. If you go interstate, they're between states. So you're estimating values between data points. And you would expect that to be usually reliable. If it's a good fit, the formula, the mathematical model, then why shouldn't values between the points that you've measured, on which you've based a good fit model, not also fit pretty well? They should, shouldn't they? And then the other one, which is naughty, is extrapolation, where we are estimating extra points, estimating values outside or extra to the data set. Okay, and you know your other work, usually unreliable. And we put the reason up there before. Let's just come down here, give it a bit more room. Usually unreliable, conditions may change. You have no idea of what happens after that last value x equals 10 or something. Okay. So are you getting the idea? These are powerful tools. You have heard modelling in many, many different areas. What are some of them? Could you brainstorm? Might like to pause the presentation here, discuss it with other people. If you do that, coming back, then what are some very, very important ones? Well, in biology or in natural science, we are looking at climate change. People are trying to model. One of the forerunners here is Al Gore, of course. Trying to make a model. What's going to happen? What's going to happen? Very hard because he's extrapolating. Right? Taking a pattern we're observing now and going right outside the data range. But I mean, it's good work to try and do that. But people's criticism is just that. That given the long term, how do you know that pattern is going to keep going? What about economic modelling? Okay, economists try to predict what's going to happen if inflation keeps going. Economic modelling is very, very difficult because patterns in the economic situation are harder to predict and harder to detect. When you have financial crises around the world, that flows through to all economies, so the models can fall over very quickly. Okay, so modelling is a very important area of practical mathematics. Okay, I hope you're getting excited that you actually can come with your technology, in this case we're just going to use a calculator, look at a set of data and start to predict what's going on there and what might go on with care, certainly. Okay, let's look at the exercises. So we've got a few exercises here from Hayes and Harris. So there's question 1 and 2. You could have a go. Pause the presentation. At any stage you can rewind me, of course. Very handy. And there's question 3. Okay, you can pause that and have a go. Question 4. I think that's all we've got there. Question 4. So go through those slowly, pausing, and if you want the solutions, I've got Hayes and Harris fully worked solutions here. So once you've done question 1, toggle on, go through to the end of this presentation, check your answer, then go back, question 2, and so on. You know how to do that. So I'll just bring these up a couple at a time. And question 3 and 4, can I get them on? Not quite. So I'll go to question 3 there. So when you want to mark it, toggle on there and so on. So question 4, all of that. So mark your work, have a bit of fun there. Okay, well, I hope you have enjoyed this part of this first topic now, where we're looking at modelling, looking at how we're going to head off and actually make this subject very, very useful. It's a utility math subject, very, very useful one. And so then the final part of this is introducing the fundamental theorem of calculus, just introducing that. That's very exciting. A lot of this you would have seen, that the calculus you wouldn't. So that's an exciting presentation. That's the next one. That's part 4, and I hope you're getting excited about seeing that one. At the moment, it's good luck with these problems. Think about it. Think about why we're doing it. And for the moment, it's cheers from me.